Good evening, everybody. How are we doing?
Good evening, Professor. How are you?
I am fine, thank you. How are you guys?
Yeah, fine. Thank you for asking.
So for summer term, most of you just taken one class, or you guys taken more than one class?
I'm taking three. I don't know.
3?
Hmm.
Wow. Okay. All right. Well, how you guys feeling about well, we only have one more week, right? I don't know how that got there. Mouse, erase, kill that, code, mouse. Syllabus. Okay, where are we? We are July 29th. Footings. Today is footings. And then we have basically one more prepared lecture after this, and then any bleed over onto the 5th, and then some time to talk about the final, and we're almost there. Okay, well, as I like to do, does anybody have any questions they would like to ask of me before we get rolling on today's lecture? All right, not hearing any. Let's get started with tonight. Tonight, we're going to talk about footings, the design of footings. So what are footings? Footings are structural concrete members designed to spread concentrated loads over a larger area to safely bear the load on soil, right? So you have concrete columns or walls or pilasters, whatever, and they collect load from above and bring it down to the soil. But if you don't spread that load out, what's going to happen? That concrete column is just going to punch right into the soil and it's not going to be able to carry anything. So it's kind of an obvious solution. You need to spread whatever axial load is coming down the building, you need to spread it over a fairly large area to safely bear it onto the soil below. Footings come in several general types. We can have a wall or strip footing. Looks like that, where this can actually be continuous for dozens or hundreds of feet, it could be. So this is just like a cut line, and a cut line, this can actually be fairly long, and that's a wall or strip footing. It is designed to carry a continuous load into the soil. We can have an isolated or single column spread footing. Looks like this. So this is a isolated footing. It is of a certain size, and it is sized so that whatever load is on this column is spread out enough that it doesn't punch through the soil below. Or we can have what's called a combined footing. So here we have one concrete footing that is bearing two or more columns on it. Sometimes these columns are close enough that the size of the footing to safely carry the load into the soil overlaps one to the other, so you just combine them into one. Or you can do it when you have a property line issue. Maybe this footing has to be right up close to this outside column, and that wouldn't work if you don't bring it back to another column. So there could be a number of reasons why you use a combined footing. We can have what's known as a mat or raft footing. Looks something like that. This is one massive footing under a whole building. Generally are very thick, useful for when soil properties are poor and the isolated footing solution would take up more than 50% of the available footprint of the building. So in other words, you go through here and you size individual footings under each one of these columns, and those footings are so big that they're almost touching each other, then it's just more economical to make it into one big mat foundation. Another reason to use a mat foundation that I didn't mention is, I don't know how familiar you guys are with the San Francisco area, but I used to live up in the Bay Area many decades ago. And I got to visit the convention center in San Francisco, the Moscone Convention Center, when they were pouring the foundations. And the foundation was a ginormous mat foundation that oscillated between 6 and 12 feet thick. And it was designed to carry pretty significant point loads coming down from the building itself. But what was interesting is not only was that mat foundation very thick, but they also had to post tension the whole foundation down through all the bay mud into the bedrock way down there, like 100 feet down. And I asked, why? Why are they doing that? And they said, well, the whole building is underground. Like the whole convention floor is underground. It's below the water table. So if they didn't anchor this thing down, the water table could actually lift the whole building up like a boat and float it. So I thought that was pretty interesting.
Professor,
Yes.
a math foundation is technically slab on grade, right?
No.
No?
No. They're similar. I can see how they would be similar, yes. But a slab on grade is just a concrete slab poured on grade, right? And generally speaking, a slab on grade is not designed to resist column loads. That slab is only like 5 to 8, maybe 12 inches at the most thick. It's not thick enough to support column loads. But more importantly, when you design a slab on grade, you don't actually design it using ACI 318. ACI 318 doesn't cover the design of a slab on grade. There's a different reference for that. And it's just based on experience for doing like warehouse floors and supermarket floors. It's really still just a concrete floor for the inside of whatever building you're doing. It's not really structural. Whereas a mat foundation is usually more like 18 to 24 to 36 inches deep. And it's taking structural loads from columns like my illustration here. And it's designed using 318 because you got to take those high point loads and distribute them out with bending and shear in every direction. So it's really kind of a different thing.
Okay.
I'm glad you asked. Thank you for the question. But yeah, they're similar in concept, but they're fundamentally different in design, if that makes sense.
Yeah, because my senior project advisor, because we were modeling a slab on grade. However, the program that we were using only offers a mat foundation option. So he basically just instructed us to treat the slab on grade as a mat foundation and just do what the program does.
Okay. No, I understand. I understand. So basically, you did a really thin mat foundation. And I am not the expert. I'm not even a novice. I've never designed actually a slab on grade. I've designed foundations, but not a slab on grade. And I do understand that it's a different reference. I don't think it's even ACI. I'm not sure if ACI has a document on slab on grade. But anyway, getting away from the point, I understand that there's just like guidelines. Like if you're doing a light duty warehouse, it's 4 inches. If you got forklifts, it may be 5 inches. If you're doing truck loading, maybe 6 or 8 inches, just various guidelines. But that's totally different than a mat foundation where you actually design for shears and moments and things like that. Okay, let's see. Oh, and we have pile caps. So pile cap, along with the piles themselves, is a foundation system. Whether these are driven piles or drilled out and filled up caissons, or even driven steel piles for that matter, whatever the pile, I guess you could use timber too. They've used timber, yeah. So whatever the material of the pile is, doesn't necessarily have to be concrete. You still use a concrete pile cap. It's just way more convenient to use a pile cap. And so what the pile cap does is it ties the tops of the piles together so that they don't try to splay out or wander or bend in any way. You want the load to just be straight down in them, like straight down into a compression element. And it also takes a singular column load and it distributes it out to as many number of piles as you need to support that column load. Pile caps and piles themselves are generally used when the soil conditions don't allow for an economical spread footing. I mean, you can make a spread footing as big as the whole building, but that might not be the economical solution. And that's generally determined by the soils report. The soils report will recommend whether or not to use a strip footing or a spread footing or go to piles. Piles caps are specialized, thick footings that transfer concentrated loads from above to a pattern of piles that bear on the soil below, generally used when the building loads exceed the allowable soil pressure, as determined by the geotechnical report. Okay, this class will focus on strip and spread footings only. Combined footings, mat, and pile caps are really more advanced topics. But there was a great class that I took. If you guys are interested and you want to delve deeper into structural topics, I believe it was a 500 level class that I took at Cal Poly Pomona a little while ago, like maybe in the year 2000. And it was an advanced class on just foundations. And that was fantastic. And that's where you would really get a lot more information about these type of topics. Okay, but for this class, let's move on. Are there any other questions? Okay, so for this class, let's talk about allowable soil pressure. For a strip and spread footings, it is generally accepted that the footings are rigid enough that the soil pressure can be found by the combined flexural formula from your mechanics of materials. For a concentric load, right, so here's a spread foundation that is D wide and it's B, the width is B in and out of the page. The load is concentric, it's right down the middle of that foundation. So your bearing pressure, which is usually denoted with a Q, that's just the way we do it. So your bearing pressure, Q, is P over A, or P over D times B, where Q is your calculated soil pressure in kips per square foot, or you could use pounds per square foot if you like. P is the load from structure above in kips. D is the length of the footing. B is your width of footing. If you have an eccentric load, where here's your foundation, but now the load is off center by some eccentricity, now your bearing pressure is P over dB plus or minus PE times Y over I, which is really the same thing as your mechanics of materials, P over A plus or minus MY over I, same thing. Where Q is your calculated soil pressure, P is the load from the structure above, D is the length of the footing, B is the width of the footing, E is the eccentricity of the load from the center of the footing, Y is the distance from the center of footing to the location of stress that you're looking for, which is usually D over 2. I is the footing moment of inertia, equal to BD cubed over 12 in feet to the fourth So the allowable soil pressure, which is denoted by Q sub A, is determined based on soil properties. In practice, allowable soil properties are determined by a geotechnical engineer and are reported on the project soil report. See, so there's a whole field of engineering that is super specialized, and that's geotechnical engineer. And gosh, if I remember right, I haven't thought about this in decades. I'm pretty sure you get your civil first. You get your civil engineering license first, and then if you want to specialize in geotechnical, you go back and take the geotechnical test and pass that, and then you can stamp things as a geotechnical engineer. I'm pretty sure. Civil engineering, I'm absolutely sure. Or structural engineering, I'm absolutely sure because I had to do it. So to be specialized as a structural engineer, you get your civil engineering license in California first, and then you get some more experience, go back past the 2-day test for structural, and now you have the authority to use the structural engineering title. Geotechnical is the same idea. So these folks are very specialized, and what they do as a profession is they go out to job sites, do some test bores, bring the soil back to the lab, do some black box magic and hokey dokey abracadabra stuff, and they come up with some numbers, and they put those numbers in a report. And we as the structural engineers look at that report and go, oh, okay. And that's what we use. As a guideline, though, you can use table 12.1 of the text instead. Because you're not actually building a real building. So just as a guideline, you can use these kind of basic numbers. Allowable soil pressures are based on service loads or unfactored loads. To compare soil pressure to allowable soil pressure, loads need to be unfactored. Okay, so let's take a step back here. I noticed on many of your homeworks, homework number 6, homework number 6 was asking for service level stresses in the concrete, service level stresses in the steel, and deflections. Deflections are always a service level phenomena, effect. Deflections are always the effect of service level loads. Nobody cares what the beam's deflection is just before it fails. What they want to know is how much is it going to deflect while I'm using the building. So many of you factored your loads and then found your deflections, and that is incorrect. You always use service level loads to find deflections. Service level loads just means it's 1 times the dead load, 1 times the live load. There's no 1.2, 1.6 or anything like that, okay? So by the same token, soil pressure is also checked with service loads. Why? I don't know. But I think it's because nobody knows what these geotechnical guys are really doing, and they want loads that are service level loads. They don't want factored loads. So when they produce a project soil report, the allowable Q sub A that they give you is based on surface levels. So it still creates some confusion because any design or check that you do against allowable soil pressure, Q sub A, uses service level loads. Any design or check that you do for the design of the concrete itself, you use factored loads. So we designed strength-based criteria for the footing with factor loads, but we design or check against allowable soil pressure with service loads. Okay, is that clear? Any questions? All right. When you're calculating soil pressures, The weight of the footing itself must be included, as well as any overburden. Overburden is just another way of saying soil on top of a footing. So for example, if this is my situation, I have a concrete footing that is 10 feet wide. I have a concrete column. I have the footing is 20 inches deep. The soil that is buried on, or not buried on top, the soil that is on top of the footing, burying the footing, is 2 feet thick. If I have an axial load dead of 125 kips, I have an axial live of 200 kips. Those loads are concentric. And this is gamma. So gamma S is the density of the soil, is 120 pounds a cubic foot. Gamma C, the density of the concrete, is 150 pounds a cubic foot. If the width of the footing in and out of the page is 10 feet, and the length of the footing is 10 feet, all other dimensions are as given in the illustration. If from a soils report we have a Q sub A, allowable soil pressure of 4,000 PSF, then is the footing as presented adequate for soil pressure? That's what we want to know. Okay, so let's figure out what our actual soil pressure is. Our allowable is 4,000. What is our actual? So the actual soil pressure is going to be the total axial load divided by the total area under that footing, plus the weight of the footing and the overburden themselves. So the axial load is the dead load plus the live load. 125 plus 200 is 325. Again, no load factors. So the soil pressure is equal to 325 kips divided by the area of the footing, which is 10 feet by 10 feet, plus it's equal to the density of the concrete, 150, times the thickness of the concrete divided by 12. Because this is inches, this is pounds per cubic foot. So to convert that, I take my inches divided by 12, and that gives me pounds per cubic feet. Or actually what that does is 150 pounds per cubic foot times a depth of 20 inches divided by 12 inches per foot gives me pounds per square foot. And that's what we're looking for. Q is a pressure, pounds per square foot. Plus the density of my soil times the thickness of the soil is 24 inches divided by inches, 12 inches per foot. I crank this all out and I get 3,740 pounds per square foot. Is that okay? Yes, it is, because 3,740 is less than my allowable 4,000, so therefore my soil pressure is acceptable. Okay, any questions about example 1?
So, Professor, if the Q is greater than the QA, does that
Yes.
mean that the soil will like go down?
It
Right?
depends. It depends on why the geotech put the limit of 4,000. And there's different reasons that they do it. Gosh, this is going back a ways, but if I remember from that foundations class, it is either that the footing itself is going to sink too far. There's a limit on how far you want to let this thing settle. All footings sink, right? You put a mass on top of soil, even if it's 2 pounds, it's going to sink into the soil a little bit. So all foundations are designed to settle some, but they shouldn't settle too much. Okay, so that's one criteria. The other criteria is one foundation, one footing compared to another footing over here that's so far away, you should not have too much differential deflection. And that's actually a lot more critical. If the whole building goes down 2 inches, okay, who cares? The whole building went down 2 inches. Who's going to notice that? But if one part of the building goes down an inch and the other part of the building goes down 3 inches, that's really going to be noticeable because it's going to bend all the beams and everything's going to be canted by that differential deflection. So that's way more critical. So that's the second criteria, is the differential deflection from one footing to another footing. The third is that the soil can actually fail itself. The soil can fail. And what happens when the soil fails is it forms like this big semicircular shear cone. And when it fails, it's going to fail on one side or the other side, and the whole footing tilts. And it takes a big chunk of soil and it shears across this face, and all that soil pounds up over here. So what you end up with is a big mound of soil over here and a foundation that is completely tilted. I mean, like 45 degrees, 50 degrees tilted. So your whole building has fallen over. And that can happen. I've seen some photos of it. It can actually happen. So you can actually have a foundation system utterly fail and the building falls over. Now, I think that's a lot rarer than having differential settlement problems, but it can happen. Does anybody know how bad this settlement thing can get? Any ideas? Anybody know some famous examples?
The Leaning Tower.
The Leaning Tower of Pisa, the world's most famous example of differential settlement. Absolutely. You guys know the story of the Tower of Pisa?
No.
Okay. This is one of our last classes. We have time to chit chat, right? The Tower of Pisa was constructed in 1100 something, 1200 something, 1300 something, somewhere around there. But it was a common design of churches in Italy to have the basic cathedral or the church structure itself, and then to have a bell tower. And the bell tower was like its own structure aside from the church. And so they would make a foundation, and then they would build, and the foundation back then wasn't concrete. It was like blocks or wood or something cribbed up from the soil. And then they would just start building the tower. And each church tried to outdo the neighboring churches. It was really amazing. But they were competing for congregation. They were competing against each other. So each one said, well, you built a tower 100 feet. We'll make a tower 120 feet. Oh, yeah? Well, we're going to go 150 feet. They kept trying to outdo each other. And some of them fell. Some of them collapsed because they built it and they had differential settlement and it started leaning over. And once it started leaning over, gravity took over and just kept it leaning until it basically just collapsed. The Leaning Tower of Pisa was a really interesting thing because it too started leaning just like the other towers. But the problem was, as I understand it, that church, the Church of Pisa, ran out of money. So they stopped building it. And they stopped building it for like dozens, I don't know, 50 years. And so it was partially completed. It leaned over, but because they didn't keep building it, it settled. It kind of caught itself. And then they started building it again when they got more money. And when they started building it again, they saw that it was leaned over, but they built it straight up from where it had leaned over. And of course, once they started building it, it started leaning some more, but then they ran out of money and stopped building. So time is the key element there. It had time to go through all of its deformations and leaning before they built it too high. And they kept repeating this process, build a little bit, run out of money, let it settle, build a little bit more, ran out of money, let it settle. And every time they built it, they tried to build it going straight up from where it was leaned over in the past. So it was really just kind of a miracle that the thing didn't collapse like all the other towers did, but it ended up in the end leaned over like 6 feet. And then under the last 200 years, it kept leaning some more and some more, and they were afraid it really was going to collapse. So then I think it was only maybe 10 years ago, they went back in there, did remedial foundation work and stabilized it. They didn't want to bring it back to straight up and down because then it wouldn't be the Leaning Tower of Pisa anymore. But they brought it back to where it was maybe 200 years ago and not in danger of collapsing anymore. So that's the story of the Leaning Tower of Pisa. Anybody know the story of the Leaning Tower of San Francisco? That's not quite as famous.
The Millennium Tower?
Yeah,
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 I heard that news.
yeah. So it didn't go over 6 feet, but it went over 14 inches. And they had to go in there and do remedial work on the foundations. Again, it's not the total deflection that really matters. It's the differential deflection that caused it to start leaning. And then lastly, probably in my mind anyway, the most famous case of too much soil deformation that I can think of are the hundreds of year old, like 300 and something year old cathedrals in Mexico City. Are you guys aware of those?
Yep. It's built on an ancient lake bed.
Correct. It is built on an ancient lake bed. It's really crappy soil, but they didn't know anything about that. So they went ahead and built this really heavy church anyway. And the church has been there, I don't know if anybody knows better than I, but at least 300 years, I'm thinking. And luckily, they did not have differential settlement. Just the whole building went down evenly, nice and even together. So the building's fine. It is just 6 to 8 feet lower than it was when they built it. 6 feet. They had to dig themselves a new entryway and put steps in there so you can walk down to the front door. Anyway, that's my detour on soil settlement.
So if that thing, it's okay if it's like the whole building, right?
Well, in some cases. In that case, what are you going to do? Tear it down? So, yeah.
Okay, but let's say it sinks like some feet. Do they need to reinforce it, or what if it keeps sinking?
Good question. It should not keep sinking because soil settlement is a time-based thing. So it takes time to settle, but after so much time, it really should stop settling. It should catch itself. So like the Leaning Tower of Pisa after, 900 years, or however long it's been around, 700 to 900 years, the soil has basically stopped itself, but in that case, it had so much lean to it that it was really in danger of falling over. The cathedral, it really shouldn't be sinking too much today, but then again, maybe it is. But for the most part, soil creep is a time-based thing.
Okay.
Okay, but I did go off on a detour. For the most part, for normal buildings, not the Millennial Tower, not the Tower of Pisa, not the cathedrals of Mexico City, for normal buildings, The original question was, what happens if you exceed this 4,000 PSF soil pressure? And the actual honest to goodness answer is, I don't know. I don't know what's going to happen. I just know that geotech said, don't do it. And so if I do it and the geotech said, don't do it, and something happens to that building, I'm going to get my butt suit off because I didn't follow the recommendations of the geotech. So this is not a materials failure. This is a legal failure. I didn't follow the recommendations of the experts who told me not to exceed 4,000. So I'm at totally my own risk. And if anything happens, I mean, if the rain gutter falls off, I'm getting sued because I didn't follow those recommendations. So you know what I'm going to do as a structural engineer? I'm going to follow those recommendations. I'm not going to put myself at that risk. So that's really the real answer. That makes sense?
Yep.
Okay. Example number 2, given. All right, so here's basically the same problem, only now I have eccentricity on my column. The column is not centered on the foundation, it's off to one side. It's off to one side by 18 inches. So I have a dead load of 100 kips this time. I have a live load of 175. My soil density is 120. My concrete density is 150. And these are pretty average common values. The depth of the footing is 8 feet. The length of the footing as shown is 10 feet. Other dimensions are as given in the illustration. The allowable soil is still 4,000 PSF. Required is the footing as presented adequate for soil pressure. Solution. So now my soil pressure is going to be equal to P over A plus or minus My over I, plus the weight of the footing itself and the soil overburden. You cannot forget about those elements. So my axial load is the dead load plus the live load, which is 100 plus 175. I get 275 kips. Eccentricity 18 inches, 1.5 feet. Just usually for foundation designs, I put everything in feet. My allowable is based on square feet, so it's just easier to have a common unit, and so I put everything in feet. Y is the distance from the center to the extreme, which is 5 feet. And my moment of inertia of the foundation is 8 times 10 to the third over 12, 666.7 feet to the fourth. So now my equation becomes, for my soil pressure, this is the actual pressure, is P over A plus P times E is M, Y over I, plus the weight of the foundation, 150 times 20 over 12, plus the weight of the soil is 120 times 24 over 12, and I get 7,021 pounds a square foot. 7,021 is significantly greater than 4,000, so no, the soil pressure is unacceptable in this example. The eccentricity must be reduced, or that footing's got to get a lot bigger in order for this to work. Any questions on example 2? Okay, example 3.
I have a question.
Yeah.
So for the load distribution, that's gonna be like a triangle at the bottom, right?
Yes. Yes, it is.
Okay, it's like in slide 43. Oh yeah, I think so. Okay, thank you.
Yep. Now, I was thinking of something, but that's too complicated. Yeah, no, it's just a triangular pattern like you would get from mechanics of materials. Okay. Example number 3. Here we have a strip footing. So that what that means is the footing is B wide, but it is basically considered infinitely deep in and out of the page. This element here is no longer a column. This is a concrete wall that is infinitely long in and out of the page. W is a linear load kips per foot. Okay, so that's the difference between this and what we just did. This is a strip footing supporting a wall load. The dead load of the wall is 5.5 kips per lineal foot. The live load is 2.5 kips per lineal foot. Soil density is 120, concrete density is 150. Other dimensions are as given in the illustration. From the soils report, I'm allowed 2,500 pounds per square foot. Required, design the width of the footing B, come up with a dimension B to safely support the loading as given. Solution. Okay, so for strip footings or wall footings, we're going to do the same thing we did for one-way slabs. We're not going to look at an infinite long wall or footing situation. We're just going to design for one strip of the whole system that is a convenient 12 inches or 1 foot wide. Excuse me, sorry. Okay, so we're gonna, and that 1 foot is in and out of the page, right? So the 1 foot high is the thickness of the footing. B is an unknown width of the footing. I'm talking about a design strip that is 12 inches in and out of the page. Q equals W over B plus the weight of the footing and the overburden. So W is 5.5 plus 2.5 kips per lineal foot is 8 kips per lineal foot. Again, no load factors. Solve for required B. So Q, again, is equal to W over B plus the weight of the footing and the overburden. Has to be less than or equal to the allowable 2,500 PSF. So then I can write my equation this way. 2,500 PSF is equal to 8 kips per foot divided by B plus the weight of the concrete footing, which is 12 inches thick over 12, plus the weight of the soil, which is 12 inches thick over 12. And I can solve for B, right? So I solve this number, and I bring B over here, I bring the 2,500 over here, and B then becomes 8 kips per lineal foot over 2,500 minus 150 minus 120 pounds per square foot, and B solves to be 3.587 feet wide. And I'm not going to build a footing that is 3.587 feet wide, so I may choose 3'9" or maybe just round it up to 4 feet wide. That would be adequate. Any questions on example 3? Okay, allowable soil pressure. In lieu of a site-specific soils report, California Building Code does allow the following presumptive load-bearing values, and these are really conservative. They're really, they don't want people trying to save money by not hiring a geotech and just following random values in a code book. But if you get into a situation where you got to assume something and you have no information whatsoever, then you can follow these. If you are building on top of crystalline bedrock, basically this is like you're building your house on top of Half Dome, then you can use 12,000 pounds a square foot. How often do you do that though? Many of us are not thinking about building our summer cottage on the top of Half Dome, so I'm not sure how useful this may be, but this is the upper limit This is like the very best scenario you can possibly think of, and which is building something on top of solid granite rock. Or you could be building on top of sedimentary or foliated rock, right? This is more like sandstone or limestone or shale or something like that. And wow, okay, I get 4,000 PSF. What if you're on sandy gravel? I think that's supposed to be gravel. On top of sandy gravel and or gravel, you get 3,000 PSF. You can get sand, a silty sand, a clayey sand, a silty gravel, or a clayey gravel. These are all technical terms, and they actually mean different things. You get 2,000 PSF, and you could build on clay, sandy clay, silty clay, clayey silt, silt, and sandy silt. I'm glad I didn't say clayey clay or sandy sand. That doesn't exist. But with these, again, these are all actually technical classifications of soil. Any of these will give you 1,500 PSF. Generally, a site-specific soils report will produce much better allowable values than these conservative minimums. In my practice, what we normally see in the LA area for excavated shallow foundation systems, so that would be a strip footing or a spread footing, what we normally see is somewhere in the order of 3,500 to 5,500 PSF is allowable. That's pretty normal. Okay, so let's talk about strip or wall footing design. When the soil pressure is checked or designed using allowable stress level loads. So while soil pressure is checked or designed using allowable stress level loads, the concrete design for footings is used with factored loading. Okay, I know this can be confusing, so please follow along, follow these examples. The examples we just did, example 1, 2, and 3, fundamentally what we did is we checked soil pressure. So there were no load factors. Those were all service level checks. But when we get to designing the foundation itself, we need to then move from service level loads to factored loads, because all concrete strength design, not deflections, not cracking, strength design is based on factored loads. So to begin the design process, we must find Q sub U, the factored soil pressure. Q sub U equals the factored line load WU divided by the footing length width, unless there's eccentricity, which that has to be added to. So again, we're talking about a strip or wall footing, and we assume we have already sized the footing width based on the allowable soil pressure. Now we need to factor the load and find Q sub U, the factored soil pressure, so that we can find the moments and shears on the foundation itself. Okay, so that's where we're going. Q sub U does not include the footing weight or the overburden of soil. Again, confusing, but Q does include the footing weight and the overburden of soil. Q sub U does not. Why? Because when we're trying to find the shear and moment on the foundation system, the weight of the foundation and the soil above it passes right through the system. It puts the concrete in a little bit of compression, negligible, but it doesn't add any shear or moment to the system because those loads go right through it to the soil below. So when we discount the weight of the foundation and the soil, we are only looking at the factor WU force that has to get spread out to this QU force, WU causes shear and moment. The shear diagram looks like this. The moment diagram looks like this. QU now becomes the load effect that we're going to create the shear and moment diagrams for the design of the concrete footing. Notice that I have this dotted line here, and I have a dotted line here. We'll get into that in a sec. Or we'll do it right now. Notice that the wall above creates near infinite stiffness directly below. So right here, that foundation has to resist shear and moment. Right here, this is a wall. So the stiffness of this concrete is almost infinite through here. You're never going to get the system to shear right through the middle of the wall. It would always shear out here where the foundation is on its own. And also, you'll never get this thing to fail in bending right through the wall. It's just not going to do that. So that's why I don't bother checking what the moment or the shear is right inside the wall, because it doesn't matter. It's not going to fail inside the wall. It's going to fail outside the wall. So my shear diagram is only to the outside face of the wall. My moment diagram is only to the outside face of the wall. Does that make sense? Does that not make sense to anybody?
Yeah, it's clear.
Okay, thank you. Because the shear crack propagates down from the face of the wall at a 45-degree angle, the maximum shear load V sub U is found at a distance D from the face of wall. And this is dictated by code. So here's my foundation system. I'd load it with a WU as a wall load. It's resisted by QU, which is the soil load. And if it's going to fail, it's got to fail through a crack pattern that looks like the red lines. So what the code says is let's check VU that is at a distance right here, D, from the face of the column. Similarly, the maximum factored moment is found at the face of the wall. So this is the face of the wall there. We're going to use this MU at the face of the wall. Now that VU and MU are defined, okay, so we defined VU is your shear force at a distance D from the face of wall. MU is your moment at the face of wall. Now that we have defined these things, we treat a 12-inch wide strip of footing as a singly reinforced rectangular section and designed for flexion and shear. So remember, this is a wall, so we're considering a 12-inch wide section of this footing down here. So if I was to cut this and look at a section, that section, kind of look at it from a side view, it's going to be H deep, as this is H deep. This beam is as long as this is long, but it's 12 inches wide, because we're only considering a 12-inch wide section for design. So in and out of the page, we're designing a beam that is 12 inches wide. Many times with such a short span length, a narrow strip, a short span length is this length here, shear will control. Most times shear controls the design of these foundations. Typically, the depth of the footing is controlled by shear, and then the flexural steel is sized based on the required depth for shear. So as it goes, usually we figure out what VU is first. We figure out how deep the foundation needs to be to satisfy VU, and then we figure out what D is based on that and design for MU. The longitudinal steel, that steel that is in and out of the page in this illustration, is sized by minimum temperature and shrinkage requirements. The minimum development length of the flexural steel must be checked as well. For footing design, it is usually or generally unfeasible or uneconomical to use shear ties. Therefore, the strength of a footing in shear is PVN is equal to PVC. In my short career so far of 26 years, I have seen one foundation that has shear ties in it. One. So that's pretty uncommon. And that was for a very special moment frame type situation. PVN is equal to PVC, which, as we learned a few weeks ago, is phi times 2 times lambda square root f prime c BD. There is no axial load on this foundation in the longitudinal direction. So you don't get any help from axial load. So we just revert back to the conservative 2 square root BD. Though footings are rarely, if ever, poured with lightweight concrete, that didn't really read so well, but let's just say footings are rarely, if ever, poured with lightweight concrete. So lambda is usually ignored. Why would you pour a foundation with lightweight concrete if lightweight concrete is about 60% more expensive than regular weight concrete? And the answer is you don't. There's no advantage to it. You don't really care how much the foundation weighs. That's not where all the weight's coming from. The weight's coming from the structure above. So it would be silly to try to lighten up the foundation system in order to make the footings smaller when you could just make the footings a little bit bigger and use hard rock. And it's still a lot cheaper than using lightweight concrete. So basically, I've never heard of foundations being made of lightweight concrete. So that means lambda is equal to 1. So basically from henceforth, lambda is going to be ignored and just is assumed to be equal to 1 for foundation design. Normally, you would need shear ties if VU is greater than 1/2 PVC, like we learned a couple of lectures ago. But ACI 318 section 7631 has an exception. And that exception allows that you do not need shear ties as long as VU is less than PVC. That exception is, there's a few reasons for the exception, but the main one is foundations. So if you're designing a foundation, then the exception applies. You don't need to worry about this 1/2 PVC. You just need to be sure that you have enough strength to cover the load that you're putting into the foundation. For wall or strip footings, B is taken as 12 inches. For isolated or spread footings, B is taken as the actual footing width. Footings are concrete cast against the raw earth, and so the reinforcement in the footing needs more corrosion protection. ACI 318 table 20.6.1.3.1 specifies 3-inch cover minimum of 3-inch cover is required for footings. Therefore, H is going to be assumed to be equal to D plus 3.5 inches. Why 3.5? That extra 1/2 inch gets you to the center of the bar, and the 3 inches is your minimum coverage for corrosion protection. Footings are exempt from the minimum steel requirements of, remember these two guys from our beam? Well, they're exempt from these two, but they must meet the minimum for temperature and shrinkage requirements of ACI 318.764, which points to 24.4, table 24.432, gives the minimum ratios of reinforcement to gross concrete area as for deformed bars, Fy less than 60.002, and for deformed bars or welded wire mesh, greater of 0.0018 times 60 over Fy, or 0.0014 as a minimum. This all came, remember we saw this before in our one-way slab lectures. Well, they apply to foundations as well. I've seen some designers will choose to use the minimum equations for flexure, which is these two, but the code minimum will be followed for our examples. That's more of a office practice. Say, well, we're going to put in this minimum. We know it's not a beam, but what's the big deal? Other designers say, well, that's not what the code says. The code just says this, temperature and shrinkage is your minimum. Okay. What do you say we do almost a 10-minute break, and let's come back online at 6:10. So I'll see you at 6:10. Okay, update. I'll be back in 2 minutes. Okay. We are back. Is anybody there?
Yeah, I have a question, Professor.
Awesome. What's your question?
So you mentioned about the lightweight concrete, right?
Yeah.
But isn't it that one is factored by the when we are solving for Q? So it's like when you use a lightweight, you have less the density for concrete when
You
we're solving
do?
for Q.
Yes, you do. Yes, you do.
So
So when you're comparing Q, the actual soil pressure, to QA, the allowable soil pressure, then using the lightweight concrete does reduce, but not by very much, but it does reduce your soil pressure. But remember in the examples that we just did, the contribution to the soil pressure from the foundation itself was somewhere like 150 to maybe 300 pounds per square foot out of a capacity of 4,000 pounds per square foot. So it's like less than 10%, maybe like 8%. But here's the thing, lightweight concrete costs like 60% more than regular concrete. So instead of using lightweight concrete, if your soil pressure doesn't work, instead of using lightweight concrete, which all it does is it takes like 300 pounds per square foot of soil pressure and reduces it to like 200, what would be 130, 260. So for 60% more cost, you're saving 40 pounds a square foot. If you're not making it on your soil pressure, make the footing 6 inches bigger. And that's way cheaper than making the entire footing out of lightweight concrete.
so it's not like worth it to use that material.
Absolutely not. Not even
Okay.
remotely close to worth it. Now, it's a totally different story if you're talking about elevated decks. There are times, there's a lot of times when going to lightweight concrete really helps the overall structure, especially in seismic country where the structure itself, the mass has to be resisted for earthquakes. So that does make sense. In a lot of cases, that makes a lot of sense, but not for the foundation, because the foundation is being supported directly on the soil, not by columns or shear walls or other elements.
Okay.
Okay, let's go to example number 4. So this example given, we have a concrete wall and the load is WU. So these two give you a clue that this is infinitely long in and out of the page, but it has a discrete width to it. The strip footing supporting a wall load The wall load is 12.5 kips per lineal foot dead, 7 kips per lineal foot live, and the soil pressure, the concrete strength is 3,000 PSI. Rebar is 60 KSI. The wall is 12 inches thick. That's this thickness here. And the soil density is yet again 120 pounds a cubic foot. Concrete density is 150 pounds a cubic foot. Other dimensions are as shown in the illustration. The allowable soil pressure is 2,500 pounds per square foot. Required. Design the width of the footing B, so come up with B to safely support the given loading, and then go the next step. Design this footing for shear and flexure. We don't know what H is yet. We don't know what B is yet. So it's going to be a bit of an iterative process to get to an acceptable design. Solution. Okay, so for strip footings, we designed the footing in a 12-inch design strip. Again, that's in and out of the page. The first step is to, and I know this isn't a real word, but it's most appropriate, guesstimate. We're going to guesstimate the depth of the footing. Let's try H equal to 12 inches. It's just a guess. And, you know, there's several overlapping variables in this, so there's really not a better way to do it. When I've done this in practice, I've designed real footings. This is how I do it. I just kind of use experience and say, I don't know, 12 inches? All right, let's find out. So we go Q is equal to W over B plus the weight of the footing and the overburden. W is 12.5 plus 7 is 19.5 kips per lineal foot. There are no load factors because we're checking against soil pressure. Solve for the required B. Q is equal to WB plus weight footing plus the overburden, which has to be less than my allowable 2,500 PSF. And so I set up my equation. The allowable 2,500 PSF is equal to my actual load divided by the width of the footing plus the weight of the concrete times 12 inches thick, because I guessed 12 inches thick, plus the weight of the soil times 12 inches thick, because it says 12 inches thick. What do I get? I get that B, I solve for B, and B is equal to 8.74 feet wide. So I'm going to say, let's make it a 9-foot wide footing. All right, so now that I know that it's going to be a 9-foot wide footing, let's calculate our shear demand VU. So here's my situation. Here's my factored load now, my factored soil pressure, and we need to calculate what VU is at this location. I don't want VU at the face of the column or the wall. I don't want VU out here where it's something else. I want it precisely at a distance of D from the face of wall. So I have to factor this because now we're talking about concrete design, not soil pressure, concrete design. WU is either 1.4 times 12.5 kips per foot, 17.5 kips per foot, or is 1.2 times 12.5 plus 1.6 times 7, dead load, live load. That's 26.2 kips per lineal foot. That controls. So my factored soil pressure is 26.2 over a 1-foot wide strip by a 9-foot long or wide footing. That gives me 2.911 kips per square foot. Now, notice QU does not include the weight of the concrete foundation. It does not include the weight of the soil because these elements go clean through. They do not put any shear into our footing. Also, I am not concerned about QU compared to my allowable QA. QA was 2,500 PSF. I don't care that QU is 2,900 PSF and greater than QA because it's apples and oranges. QA is my allowable soil pressure QU is my factored soil pressure. They are not even in the same ballpark. Okay, everybody clear about this? Any questions about this? Okay, so D is equal to H minus 3.5. Why 3.5? Because it's 3-inch cover for soil, plus we just assume that the bar to the center of the bar is 1/2 inch. We could refine that later as we get through our design, but for now, 3.5 is a good round number to use. So I chose a foundation 12 inches thick, minus 3.5 inches gives me a D of 8.5 inches. So VU is equal to the soil pressure, factored soil pressure, times the width of the beam, which is 1 foot, times, now here's where it gets a little tricky. What we're multiplying this times is this length right there. In fact, I can draw that in if you like. From the edge of the foundation to this point right there. That's the distance I want. How do I get this distance? Well, I take half of the width of the footing there. That's 9 feet over 2. So that's half of the footing. I minus out half of the wall. So there's 12 over 2. I take out. And then I subtract out from the face of the wall to my critical section is the dimension D. So then I take out D. And then these are divided by 12 and 12 here and here just to keep everything at feet. Okay? So shear is found by this distance here, and I get that distance by half of the overall footing minus half the wall minus D. That's what this is.
Professor?
Yeah.
So there's 2 D's over here. The one is from the center of the rebar up to the very top of the footing,
Yes.
and then the distance where you want to find from this corner to that where we looking for the shear.
That's the same D.
So they're always equal?
Yes.
Okay.
Because that's what they did. They basically said, okay, this depth is something that we designed. This failure plane is a 45 degree. So if this is 45 degrees, then this depth here is equal to this length here.
Yeah, that makes sense.
They basically just drew a isosceles triangle or equal leg triangle. And they said, all right, well, this is the depth and this is the width, and we can calculate that because we know what that is, and makes it doable. It makes it simple. So yes, no, you're right. D that we know of is defined as the concrete in compression to the center of the steel in tension. That's the D we've been talking about all along. But for measuring where to get the shear, we go a distance, that same distance, we just take it horizontally from the face of the wall to our critical section. Okay, is that clear, everybody? Does that make sense?
Professor?
Yeah.
Could you repeat where that middle 12-inch came from?
Sure. The wall is 24 inches wide. No, I'm sorry, the wall is 12 inches wide. So from here to here is 12 inches. So to get from the center of the foundation to the outside face of the wall here, that distance is 12 over 2.
Okay, thank you.
Sure. Okay. Okay, so when I calc this out, my shear demand VU is 9.6 kips. That's the number I get. And so if I looked at this chart here, the shear would be 0 at the outside edge of the foundation because there's no load on it yet. The shear would be something greater right at the face of the wall, but we don't need to worry about that. We just find what that shear is at that dimension D from the face of wall, and that's 9.6 kips. Then we compare that to our capacity. Our capacity is phi VC, which is phi 2 times, remember we're going to ignore lambda, so 2 times square root of F prime C BD. So that's 0.75 is phi times 2 times square root of 3,000 times a 12-inch wide by 8.5-inch deep piece of footing. And that capacity is 8.4 kips. Any problem there? Anything wrong? Anybody notice a problem?
VU is greater.
VU is greater than VC.
That's right. I know it's trivial, but that's the check. That's why I keep harping on you guys. Check. Phi MN greater than MU. Phi VC greater than VU. It's not in this case. It's less than VU. It's no good. Why is it no good? Well, remember, I guessed at 12 inches in the first place. That was just a total guess. So let's try again. Let's guess 16 inches. So we go all the way back to the beginning and we solve for B. Why? Because 16 inches adds more concrete weight to my soil pressure. So I need to reconfigure. So everything's exactly the same as before, only instead of 12, now it's 16. And that produces a B that's slightly bigger than it was before. Now I need 8.94 feet. Luckily, I can still use my 9-foot wide footing, so that didn't change. D is H minus 3.5, which is 16 now, minus 3.5 is 12.5. So my VU, I have to recalculate, right? Because D is 12.5 now instead of 8.5. So that makes VU actually go down just a little bit. Why? Because we got a little bit farther away from this wall. That's why. Let's see. Oh, I forgot to mention. VU is still based on 2.911 KSF, which was here. Why? Because my wall stayed at 9 feet wide. If the wall actually had to be a little bit wider, then I would have to recalculate QU to compensate for that change in the wall width. But in this case, I'm still able to use 9 feet. So that didn't change. That went right there. And I have 8.6 kips. So now I check that against my capacity, which is phi times 2 square root F prime C, 12. But now my footing's 12.5 instead of 8.5, which is a pretty good increase. And I get 12.3 kips. Aha! My phi VC is greater than VU now. So shear-wise, I have an effective design. It works for soil bearing and it works for shear. So the last thing we do is calculate our moment demand, MU. So MU is found at the face of the wall, not at DOA, but at the face. So I find MU, I take 2.911 KSF, and the equation is 2.911 times the width times the depth of the area that's being loaded squared over 2, right? So you're taking this pressure times an area is a force, and then the eccentricity of the force to the face of the wall is that distance over half again. So that's why you got to calculate. Here, I'll draw it so there's no confusion. We are looking at this area here to the face of the wall. So what is that distance to the face of the wall? Well, it's equal to half of the footing, which is 9/2, minus half of the wall, which is 6/12. So that's the distance, and then we're squaring it over 2 to find the force times the eccentricity. And that equals 23.3 kip feet, or 280 kip inches. That's my demand at the face of wall. So then we go back to singly reinforced rectangular beam design, way back to the beginning of this semester. And we find our reinforcement index, which is mu over phi bd squared. So I got 280 over phi times b times d squared is 184 psi. So I go back to my table A12, rho is 0.0032, AS required is rho times BD. There's rho, there's B, there's D. I get 0.48 inches squared per foot. If I go with a number 6 bar, then the required spacing of the number 6 bar is equal to the area of the bar over my demand times 12. So area of a number 6 is 0.44 over my demand of 0.48 times 12, and I get 11 inches on center. ACI 24433 prescribes the maximum spacing of deformed reinforcement as, and this is the same as the one-way slabs, if you remember. So it's either 5H, so 5 times 16 is 80 inches, or 18 inches. 11 inches is less than 18, so we're totally good there. And almost done. So AS, my actually provided steel is equal to the area of the bar times 12 divided by the spacing of the bar, which is 0.48 inch squared. Remember, as I've said a billion times by now, it is not good enough to just come up with an area and spacing of a bar. You must check that Phi-Mn is greater than Mu to know that this thing works. So I calculate my Phi-Mn, Phi is 0.9, ASFYD minus ASFY over 1.7 F prime CB, 312, greater than 280, so we're good with that bar and spacing. Check with our minimum steel. This is the equation for temperature and shrinkage. 0.0018, 60 KSI over Fy times B, not times D, but times H. And that calcs out to 0.346 inches squared per foot. We're providing 0.48, so we're fine there. And we have to check the development length. Why do we have to check development length? Because this bar needs to be developed at this critical section at the face of the wall. And so, as we talked about last lecture, we need to make sure that there's enough length of bar here that it can fully develop the yield where you need it at the face of the support. So we're going to check that. And remember this equation from last lecture, where lambda is 1 for normal weight, psi t is 1 for a bottom bar. This is definitely a bottom bar. Psi e is 1 for uncoated bars. Psi s is 0.8 for a number 6 bar. That's that size factor. CB is the smaller of half the spacing. Remember, I chose a spacing 11, so 11/2 is 5.5 inches. Or center of bar to the nearest face, which is 3.5 inches. Smaller of the two is 3.5. KTR is equal to 0 because footings do not have transverse steel. There's no ties in this footing. DB is 0.75 for number 6. So I plug that all in there, but this factor here cannot be taken larger than 2.5. So I changed that to 2.5, calc it out. I need 19.7 inches to develop that bar. How much do I have Well, what I have is half of the footing is 9 feet over 2 minus half the wall to get to the face minus 3 inches on this face because you got to give it a 3-inch gap there to protect it on the end. And that equals 45 inches. 45 inches provided is better than 19.7 inches required. So we're okay. We got that bar developed. Now we need to check the minimum steel in the longitudinal direction. Same equation, same result, 0.346 inches squared per foot. If I use number 5 reinforcement, then again, put in the area of the bar over your demand times 12, and you get a spacing of 10.75 inches on center. So I'll use number 5s at 10 inches on center. Final design looks like this. Here's my 9-foot wide that I found from my allowable soil pressure, my 16-inch deep that I found from shear capacity, my 3-inch cover, because that's what you need. And by design, I found that the bars going in the direction of the footing width, number 6 is at 11, and the bars going longitudinal or the length of the footing, number 5's at 10. And that's it. That's our design of this wall footing. Any questions?
For the cover, for the vertical one, is that 3 as well or 3.5?
Well, by necessity, the transverse bar has to be either on top or below the longitudinal bar. The transverse bar is the one that was doing the flexural work. That's the one we actually designed. So it should be on the bottom to give it the most advantage. The longitudinal bars, the number 5's at 10, are not required for any flexural demand. They're just required to satisfy temperature and shrinkage. So since those don't really matter, put those on top. So the 3-inch cover is to whatever bar is lowest. That's going to be the number 6's at 11. And then the bars on top of that, the number 5's at 10, are just on top.
And then, oh, when we're solving LD
Uh-huh.
and then comparing it, there's always a cover on the right side, right?
Uh-huh. Yep.
So, and for the H, it's 3 plus the radius of the steel, or is it always 3.5?
Okay. Yes, good question. In this case, D would actually be 16 minus 3 minus half of a number 6 bar would be another 3/8 of an inch. So our original assumption that D was 16 minus 3.5 actually should have been minus 3 3/8. But that's what I was saying. We don't know that until we get all the way to this stage here. And I'm not going to go back and redo all my calcs for 1/8 of an inch. So that's why I'm saying 3.5 is a good average, and it actually covers you up to a number 9 bar. If you had a 10 or 11 bar, you might actually want to revise it because you're a little unconservative at that point. But up to a number 9 bar, maybe even sneak it to a number 10 bar, 3.5 is acceptable for determining, your rough dimensions. And then you could always go back and refine it later if you needed more accuracy.
Oh, and one more question. So when we're using H is equals to 12 and then we change it to 16, the footing becomes heavier, right?
Yes.
So that's why we can meet the shear that we need to.
Well, no, the footing becomes heavier, so you have to recheck your allowable soil pressure. And if you were really close, it might bump you up to, you might have to make it wider. But when you make the footing deeper, it's not because you make it heavier that it resists the shear, it's that you have a deeper D, and the shear is a function of the width times the depth.
Ah, okay. Okay, that makes sense. Okay, that's it, Professor.
Okay. Fun fact, just a little bit of trivia here. When I took the civil exam, my PE exam in, when did I take that thing? I think it was October of 97. When I took that, you were given 12 questions for the afternoon. Each one was an essay question. So you actually had to draw drawings and write out calcs with a pencil and paper. And you were given 12. You had to solve 4 of the 12 because people are coming from different backgrounds, different fields of interest, whatever. So people had different expertise. My expertise was in structural. So of course I picked the 4 essay questions that were structural. One of those 4 was pretty darn close to the entirety of what I just did for example number 4. That was my exam question on the PE exam. So I don't know, fun fact, but yeah.
Do you need to memorize the code for this one when
No,
taking the exam?
no, heck no. Hey, no. Yeah, I don't want to get derailed, but when you sit for the exam, there's no limit on how many books you can bring into the exam. The only limit is you're given like 6 feet of fold out table. That's your space. You have 6 feet of table. And whatever you bring has to fit in that 6 feet, either on the table or under the table. And you can't take up somebody else's space. So you can't, there is some practical limit. But I saw people coming in with Home Depot carts full of boxes full of books. I was like, they were bringing the whole archival library with them into this thing. And I thought that was silly because you're going to waste so much time just trying to find the right book, let alone the right page in that book to find the answer. But I thought what I did was quite reasonable. I brought a box, I don't know, maybe 2 feet long of a box, and I filled that up with books, and I just carried it on my shoulder, and that's all I needed. And I passed, so you can do it with a box of books, but I definitely would not try to go in there with no books. You don't have a prayer if you don't have some very basic code books and some reference material. So somewhere between no books at all, which is insane, and a Home Depot shopping cart full of books. So there's a happy medium somewhere in between those two. Okay. Again, not to get derailed. Any other questions about example number 4, design of a wall footing? Okay. Simon, did you have a question?
Are you gonna answer questions about the finals in this lecture or the next one?
I was, you know what? We could do it now. I have actually enough material. We're not going to finish this lecture tonight in the next 15 minutes. I still have another 220 slides. So I was fully prepared to just stop at some convenient point and pick this lecture up next Tuesday. And then the lecture we do for Tuesday also is probably more than about an hour and a half of lecturing. So that I know that's going to bleed into next Thursday. And then I was going to spend the rest of the time that we had on Thursday to talk about the final. But if you want to talk about the final now for 10 or 15 minutes, just so you have some guidance on what to study this weekend, and then we can talk some more about the final on Thursday after we finish the last of our material to kind of fine tune how to study on the last weekend. We can do that too, if you like.
Yeah, that sounds pretty good.
All right, so we'll push the rest of this material. I mean, this is a perfectly good place to stop for tonight. We stop at square spread footings. That's slide number 306. Lecture 15, slide 306. Okay, so we'll pick up from here on Tuesday. And what would you like to ask me about the final?
It's cumulative, like from the beginning of the semester to what we're learning right now.
Yes, it is. Yes, it is. But keep in mind what that could mean. For example, when we just did the wall strip footing that we just did, for the flexural part of it, you notice that we went right back to what we learned about doing singly reinforced concrete beams, rectangular concrete beams. We used that reinforcement index, defined rho. We used rho to find the area steel. We picked an area steel. We picked a spacing of the area steel. And then we checked that phi min is greater than mu. So I don't have to ask a question again about singly reinforced rectangular beams. I could ask you a question about square footings, and you have to know something about how to do the flexural design of singly reinforced rectangular beams. See what I mean?
Yeah.
Same goes with shear. What we learned about shear for beams, you're applying to the design of footings. So just because it is cumulative, I could re-ask another question like we did on the first midterm, or I could work it into another question on the final that's about more recent material, but you got to know what you did the first half of the semester in order to answer these questions. So I could do it either way.
And is it 4 questions like last time?
Yes, yes. Yeah, it's probably 5 questions like I did last time, where 4 of them are essay style, and the 5th one is fill in the blanks. I'm thinking something, I haven't written it yet, but something like that. Because basically you have the same allotted time. The midterm was 2 hours, the final will be 2 hours. What else?
That was all my questions I had.
Oh man, that was only 3 minutes.
I
Is
thought
is
more.
it gonna be more focus on the later part,
It is.
and then so like way back to the first lecture, it's just like embedded to that question per se?
Yes, yeah, yeah. But not entirely. Because yeah, remember, there's a lot I can do with the latter material. There's a lot I can do with that, with spread footings, which I think, I gotta remember, I think homework 8 had footings on it. So there's a lot I can do with footings. There's a lot I can do with columns, because columns are fantastic. They have axial load, they have tension, they have compression, they have figuring out the phi factors, they have moments. Oh man, there's all kinds of stuff I can ask about columns. So between footings and columns, I can pretty much test anything that we did in before the first midterm. But please keep in mind, we cut off the midterm at T-beams. So that means I haven't tested anybody on compression steel yet, or anything after compression steel. So please keep that in mind as well.
There's no homework 9, right? The homework 8 is our last one.
Homework 8 is your last one, yes.
All right.
Yep, I wouldn't do that to you. Hey, everybody, time for your final. Where's your homework? Give me your homework. No, homework 8. I felt that was enough of a punishment for living. The same rules will apply. You're expected to have your computer to see the problems on Blackboard and to fill in the Blackboard, of course. But other than your textbook, your one sheet of notes, your pencil, your eraser, and your calculator, that is what is all that is expected to be at your disposal. So it's open book in the sense that you can have your textbook, but you may not have any past exams. You may not have anybody else's notes. You can't have a binder from somebody else that took the class 2 years ago. Nothing. It's your textbook, your one page of notes, your pencil, your paper, your calculator. That's it. When you're done with the exam, or the exam is done with you, when you run out of time, it will be submitted, and then you upload all your handwork so that you can get any partial credit that's due to you, just like we did for the midterm. And I think you got a pretty good sense. I mean, hopefully everybody went on to Blackboard, looked up your midterm, and saw the comments that I've given you. That's really there for your benefit, for a learning experience. So please look at any comments that I did on your midterm. And if there was any errors or misunderstanding, please correct that for the final. Okay, what else do you have? What other questions?
Is the one page front and back for the notes?
Sure. Sure. I'm not gonna, yeah, that's fine. That's fine. Just please, when you do your handwork, your hand calculations, don't do it on the back of the paper. I can't read that. Make sure it's on the front of the paper. Make sure when you take photos of it or you PDF it or however you do that, make sure it's legible. Make sure I can read it. Because if I can't read it, I can't give you partial credit. That's how it works. Okay, so is there anything else specific you need to know in order to study this weekend? That's why I wanted to give you some time now so that you don't lose a weekend of valuable time to study. If we just started talking about this on the last day of the class, then you only have one weekend. So is there anything else that I can talk about in terms of scope of what you should be looking at when you start studying?
As long as we look at the homework and understand it, we should be okay, right?
Yeah, I would say so. Yeah. Yeah. I believe the scope does include footings. I'm pretty sure that last homework number 8 has footings on it. In fact, I can check that.
It's just one questions.
Just one? Yeah,
Yeah, for
well,
homework number 8.
once enough. Homework number 8. What did I do? Yeah, that's a footing. I didn't want to kill you with it, but that's a footing. Okay, so the scope of the final is really from class number 1. But like I said, almost everything that you did on the midterm can be worked into a more recent problem. But that doesn't mean I'm not going to do anything with the material. You know, I could give you a T-beam again. I could give you just a singly reinforced beam, but I could have it as a design problem instead of an analysis problem. You know, anything like that. So go back and, you know, basically refresh yourself basically from the beginning. The first test did not have any serviceability stuff on it, like calculating deflections, for example. That wasn't on the first exam, so that's wide open for the second, the final. And again, don't factor your loads if it's a service level design check. That's something I'll be very keenly looking for. So the scope, I would say, is from flexural design of lectures 1, 2, 3, up to tonight, which is the design of wall footings or square footings, basically.
I have a question for this homework. It doesn't have a soil on top, right?
I just killed it.
Oh,
Let me see. Yeah, you don't always have overburden. Yeah, see, okay, so see how I drew the foundations flush to grade? That means there's no overburden.
okay.
Okay, and then this is actually most of the footings we do. This is kind of what they look like. There, you know, maybe there's a slab on grade off to the side here, but that doesn't change the footing. But then a lot of times there is overburden. We've had some that are buried in 5, 6, 8 feet of dirt sometimes. So it just depends. Anybody else? Any questions about scope? What to study for over the weekend? Or start studying for, I guess.
I think that's it. That's all the questions you have.
Okay, all right. Well, I think that was, hopefully that was helpful. Also, please make sure you go back and review your homeworks because I put little stickies there. I try to go through the homeworks as best I can. I try to go through your work step by step. And when I find, I'm not so much worried about calculation errors, you know, maybe that's a point here or there, but when I find errors in understanding or misunderstanding, I try to put a sticky there as to what the problem was. So please review your homeworks as well and look at the notes that I put on there to hopefully correct any misunderstandings or bad habits, if you will. For example, I know I've said this in class before, but just as an example, if you are still trying to calculate the area of steel using pi over 4 times 9/8 or something like that, instead of going to the table and looking it up, that will cost you dearly on the final. Because I've put many stickies on people's homework saying, stop, don't do that, it's wrong. So that's just an example. But please go through your homeworks and go through your midterm and read whatever notes that I've given you to try to correct any misunderstandings. Okay, if there are no further questions, we will wrap it up for tonight. I bid everybody a good weekend and we will see you on Tuesday.
Thanks.
Thank you, Professor.
Thank you, Professor.
Thank you.